Yes, okay. And this was my last question on Monday. And this is a very important thing. So I take my time to explain this whole thing very good. Okay, this is a very important thing. So we construct this thing um, from actions um, from actions to omega. And I think this was a very difficult question. Okay, but the explanation is not so complicated. So I try to make a step by step, and at the end of this class, we can discuss the implication of this and why it's an important thing for financial maths and for a portfolio risk management and something like that. So for probability and stochastic calculus and Markov chains and something like that. So the first question is the I can say this is the intuitive problem. Okay, so I try to to make some intuition about this thing. The intuitive problem. No, sorry. Um, this is uh, this is the thing. Okay, so before any formalisms, we face a basic question. Given a random phenomenon, how do we rigorously assign numbers, tell probabilities to events? Okay, this is the problem. And the answer requires building three objects together. And this is this object. And each one solves a specific problem. Okay, so I have a random phenomenon with have a random thing. Okay, this is the problem. And this random thing, for example, a coin flip, a stock price, T, all price parts of a stock, one default, I don't know, some of the things. And, and the question is, this is the whole thing. How how would you um, how do we, and this is a question, sorry, how do we assign uh, numbers? Okay, numbers, and this number is called probabilities. Probabilities uh, to these events. This is the question. So do these events. So um, I have, for example, a coin flip. Okay, this is a coin flip. This is the coin flip, and okay, I have two options. Okay, I have two options. I have um, I have H and T. Okay, or 1 0. I don't know. And I say, well, the probability of option one is 1/2, and the probability of option T is 2 1/2. And the question is, why can I do this? Okay, this is yes, this is something trivial in this example, but why can I do this? Or I have a one default. Yeah, this is the probability, and I say, okay, 0 is default, 1 is no default, and what is the probability of this? Probability of default, this is something like 0.8. The probability of not default is 0.2. Okay, also this is the sum of these probabilities is 1. Okay, this is 1, this is 1, and this is a very important thing. We see this later. But why can I do this? This is the question. Okay, we need to a structure to explain those things. So and and the answer requires three objects. Okay, objects together, and this is the probability space. This is the thing. Okay. Okay, so this is the intuition. Intuition is this question: why can I do this? Huh? Why can I do this? Under what conditions can I do this? Can I do this always? The question is no. And this is a very important question that some books, some professor doesn't explain. Okay, and this is very a good problem. So, okay, two. This is the sample space. Okay, this is the sample space. Omega. Well, we have these three objects, and omega is the capital omega is the sample space. And what is the sample space? Well, the sample space is the set of all possible outcomes of a random experiment. Okay, in this example of coin flip, this is the sample space. I can do the coin flip. The sample space is the thing, is the R and P in one default, in one. There are not probabilities. Okay, this is a very important thing. A very important thing. Probability is a measure, a function, and this is a z. Okay. Yes, we define the function from asset R to asset V, but in this case, there are events. Okay, not probabilities. Then bond default, I say, well, omega is 0 and 1. Okay, and this is the whole thing. For example, a stock price. Okay, at a time capital T. The sample space omega is 0 to infinity. Okay, the stock price $10, $100, $1,000, and this is the positive real life. Okay, this is the sample space. So and we say, well, omega, the elements from omega, from capital omega are omega 1, omega 2, so omega n, and this are the sample points or elementary outcomes. But this is the sample space. Okay, and this question, I can say, well, omega 1 is H, and omega 2 is T. And in this example, we have a problem. Omega 1 is 0, okay, but omega 2 is 0.0000001, something like that. There are infinity points, okay? So this is a very good question. And this is purely a Z-theoretic object. No probabilities lives here yet. This is the important thing, okay? But I try to make a good things, okay? So add, for example, to this thing is not trivial. This thing, yes, it is a trivial thing, a trivial question, but this thing, one default, is not trivial, okay? And I have a very good example to say, okay, we must be careful, okay, with this construction. For example, I try to explain all price parts of stock. Okay. What is the omega? The events. Well, in this question, omega is the strength. Okay. This is the thing. Okay. This is some functions and so t r, and this is the bullet problem. Okay. This example illustrates why this construction must be careful. Omega can be uncountably infinitely. Okay, and naively trying to assign probabilities to every possible subset leads to contradiction. This is the Vitali, but this is so for measure theory and it's very difficult. So, but I try to say, well, this is not trivial. Okay, and then come the question, which subset can have probability? Okay, yes, we have the space of the events. This is the fourth object of this construction. And then we need to say, well, we have events. Which event can have probability? And this is the G object F. Okay, so I'm trying to say this is the sigma algebra. This is the sigma algebra F. Okay, and the question is which subset can have probability? Reality. And this is the main question. So we say, okay, the sample space is the space of the events. I make something, coin flip, or something like that, and in this space, omega, I have all these events. Okay, coin flip, ha, t, and something like that. Okay, but not even a subset of omega can be assigned a probability. Okay, and yet we need to specify a collection F of measurable subsets. It's a very important question, and the subset we are allowed to ask about. Huh? Okay, and this is the whole question. Why can I do this and why not? Right? So we have omega events. Okay, so coin flip, for example. And then my question is, okay, which event is a subset of omega can have probability? Okay, and this is the question, and this is the sigma algebra. This object F, okay, say to us, yes, you can assign a probability. You cannot assign a probability. This is the question. So we need some definitions. Okay, definition. A collection F, and F is a subset of Q omega. This is a power set. Is a sigma algebra. It's a sigma algebra. If it satisfies, and this is actions. Okay, this is option one. Contains the wall space. This is trivial. Okay, the wall space, and that's what's in it. This is okay. Omega is a subset of F. Okay, omega exists on F. Action 2. What do you think is this action 2? Yes, this is not trivial, but this is closed under complementation. Complementation. What's this mean? Okay, so R exists on F, then the complement of R exists in F. Okay, this is a very good thing. Okay, this is a very important thing too. And this is I try to action F1, F2. This is the action F3. Okay, this is closed under countable unions. Countable unions. Countable unions. Okay, what's that mean? So, I have some objects. Objects are part of F. Then the union of all these things are two in F. Okay, there are the three actions, and they are very important. Okay, and so I try to make this. Okay, if you do probability, you can say, oh, I recognize this thing. Okay, from these three actions, several properties follow immediately. Okay, and this is a very important thing. What are those properties? So I can say some properties. Okay. The first is the null space is element F. The question is why? Well, action one says action two says closed on complementation. Ah, I say that omega complement is the null space. Okay, so and 10 is a part of F. So two closer is closer on the countable intersections. Intersections. What's also meaning? So this thing. Okay, this thing as a part of F. Why? This is the De Morgan. Why De Morgan? The proof is why De Morgan. This is set theory. Okay. And three, okay, it is clouded under countable intersection and it's clouded under sets different. And this is a very important thing. So clouded under sets different. I try R R not V is equals R intersection V V complement, and this is a part of F. So there are some properties, and yes, I say it is very very easy, but it is not trivial. Yes, I know this is a theory, but I try and something to note and something like that. Okay, the proof of all these things. If you have a book, or if you have access to internet, I think this is true. Then you can find all this properties very easy. Or you can ask me and of course I give you an good, I think, answer. Um, okay. A good answer. And this is a very important thing. I try so. Okay. this thing is a measurable space. Okay, this is a measurable space. Okay, and this is a very important thing. And we have with this the Borel sigma algebra. If you take a course of measurement theory, yes, I know that the most people in this course comes from financial maths. This is the idea. But if you are a mathematician and if you take measurement theory, if sigma is equals the real number, for example, asset price, then the natural choice is the Borel algebra. Okay, the Borel algebra contains all open intervals. It's includes all open sets, closed sets, countable units, and the sections. Yeah, so essentially everything one encounters in practice. Okay, but this is another question for another topic. Okay, so we have this thing. Okay, yes, we have the event. Okay, and I know that if my event is the set of all my events, okay, respects these properties, can I assign a probability? Okay, this space is measurable space. Okay, good. So, this is the probability. This is the probability measure. Probability measure P. And this is the Kolmogorov actions. Kolmogorov actions. Well, this is for I'm trying to okay. Well, okay, now we assign numbers to events. This is the idea. Also, think on this construction. First construction, the sign for event, omega, we have the event. Coin flip, one default, and something like that. Two, we have rules for this event. And these rules are F, okay, and it's very important to say, okay, which type of events collections can I measure? If these things if this thing respects these laws, can I measure? And then come, how can I measure this? Okay, and this is the probability measure P. Okay, so the first question is, what is the probability measure? Well, a probability measure is a map. It's a function. The function comes from F to 0, 1. This is the probability measure. Okay, this is the classical picture. This is a map F. Okay, so this is my thing. I can say, well, I have subsets, something like that. Okay, this is a 1, a 2, and something like that. And then this map P assign a number between 0 and 1. These are not discrete. This is continuous. Okay, and then the whole question and this function moves satisfying the three Kolmogorov actions. Kolmogorov actions, and I have a comment of this. The most classical thing is to say, well, P is a function from omega to 0, 1. Okay, And this is this example. I say, well, conflict, what is the probability of power t? 1/2 and 1/2. And this is the function, okay? This function, the function p comes from ht to 1/2, 1/2. Okay, but it's correct to say from omega to 0, 1. No, it's not correct. Why? Omega are the events, but I don't know if I can measure this event. So this is so a tricky question, a theoretical question, but this is not 100% correct. Okay, so I tried the wall definition. Yes, if you do financial maths or something like that, this is good. It's a good option and not problem. But if we take the correct instruction, the measurable probability comes from f to 0, 1. And we have some actions. Okay, so the action. This is the action. Kolmogorov 1. This is the known negativity. The probability of an event is positive or 0 for all elements in F. Okay, this is the first question. This is the action 2. The probability of omega of all the events is 1. And this is a very important thing. I have a omega, and omega as omega 1 is omega n. Okay, and then try to measure probability. I have all the events and the sample sets, and the probability of all this event is 1. This is a very good thing. Okay, and so I tried to to say this, but this is something clear, something trivial. And now the action 3. This is very, very important. The action 3 is the sigma additivity or the countable addition. And I have, okay, if R, there are subsets of F elements, and these elements are pairwise this point, here intersection I showed is a null space, and here is not short. Then, and this is the classical rule of probability, I do this with red. So the probability, the measured probability of the union of all these things is equal to the sum of the probability of each element. And this is a very I do this with red. And so it has the probability of omega is equals 1, and the probability, this is then the non-negativity, so the probability of all elements are positive. Okay. And then, okay, and then we have these things. We have this thing is a probability. Is a probability space. Okay. This is the probability space. And action K3, this is this action. This is the countable additivity or sigma additivity is the crucial one. Okay, finite additivity alone is insufficient for current theory. Sigma addition is what allows limits convergence theorems and the entire machinery of analysis to apply. Okay, and yes, okay. Yes, we have the question. I think this was a good question last Monday. Sorry for that. But now we have all this Flask theory. Okay. So we can say maybe what are the consequences of actions. Okay, and to end this class, I say, well, this five this is the consequence of the action. Jetzt, okay, also we can measure things even, okay, consequence of actions. What are the consequences? The classical probability rules, okay, so the probability of null space is 0. The probability of the complement, that's a very important thing, is 1 minus the probability of R, and think on that. This is my space, okay? From 1, and I measure. I know that the probability that's P from omega is 1. Okay, this one, this probability is 1. Okay, and what is the probability? For example, this is R. What is the probability of this thing? Well, what I know, it's the who is tasked is the thing, okay? That a complement is a part of the whole thing. So what can I say? Well, this is the probability, this measurable probability is 1. Okay, so the probability of this thing, of this is a complement, is 1 minus the probability of this thing. So I have how to control and how to measure probabilities of complements or something like that. This is a good thing. For example, the probability of a boundary fall is 0.8. Okay, the probability of R is boundary fall is 0.8. What is the probability of not boundary fault? Well, the probability is 1 minus 0, 0.8. And this is this rule, this application of this rule. But the question is, why can I apply this rule? Okay, I know that the complement is a part of the whole thing. Okay, so pay attention to these things. It's very important. And well, classic thing, the probability of the union of something is the probability of R plus probability of B minus the probability of the intersection. This is something clear. I am why it is. Well, I have, for example, this, and I have R and V. What is the we have R? This is make some partitions in this, and this is, for example, R, and this is V, and I measured this probability of R union V. What is R union V? Well, this is what R union V is. This thing. Okay, and then I measured this and measured the probability of this, and the intersection. I is which elements are repeats in each subset. Okay, and I subtract this. This is a very important concept. So and then some classic things. If R is the subset of B, then the probability of R is not probability of B. Okay, it's smaller than probability of B. And we have the fundamental continuity of measure. Okay, if I have a increasing frequency of set, then the probability of this thing converges to the whole probability of R. And this is if this is the notation, and this is the continuity of measure. So this was the comment. Okay. So this was I think all. This was a good question, a good answer, and so and please think on all those things. Very important.